3 alpha. So the scalar product U is equal U, scalar product V is equal to 0 if and only if alpha is equal to 0. The third part is computing the Euclidean norm of V. And this is the square root of 1 plus 1/4 plus 9, which is equal to the square root of 10.25, whatever it is. Then we have operation. So remember, what are the operation character between vectors? It's like natural operation in vector. Actually, those operations are the ones who give Rn the structure of a vector space, what is called a vector space. Sum and multiplication by a scalar, or by a real number. So combining both operations gives what is called a linear combination. We have two vectors, and say A and B, and two scalars, say S and T. The linear combination from S, T, A, and B is, for instance, T scalar product with A, or A multiplied by T as a scalar, plus S multiplied by B. Since we know both operations, we know how to combine them. The resulting vector is called a linear combination. Obviously, there are infinitely many possible linear combinations of two vectors. Actually, what is the geometrical representation of a linear combination of vector? Are all the vectors that can be obtaining summing expansions, contractions, and what? Reflection of the two given vectors. And actually, the set of all linear combination, I'm going a few slides ahead, but we will see that the set of all possible linear combination of two given vector is what is called a linear space, or a linear subspace, in this case of Rn. But we have as well a concept which says that give the information provided by a group of vectors is not redundant. This property is called linear independence. So the vectors are a group of vectors, a family of vectors, which simply say some vectors are linearly independent if there is no linear combination of them yielding the zero vectors origin. Why it's called linear independence? Because this property is equivalent to say that it's not possible to write any vector of the family as a linear combination of the other vectors. And why is that? Because let's start from this definition and let's play a couple of minutes with this. So there are no scalar. I've been hitting a moment that we need those scalar not being all zero. So we need at least one scalar different from zero. Why? Because it's clear that if we multiply any vector by zero, we obtain zero. So the sum of zero is zero. It's not very interesting. So assume there exists. So even better, assume V1, V2, Vn are linearly dependent. So there exists lambda 1, lambda 2, lambda n, not all zero, such that lambda 1 v1 plus lambda 2 v2 plus lambda n vn equals 0. So unless we rename the vector, let's make it simple. So assume lambda 1 is different from 0. Then you can write then V1 is equal to what? V1 is lambda 2 divided lambda 1 V2 plus lambda 3 divided lambda 1 V2 plus, sorry, it's minus, here it's minus, and here it's minus lambda n divided lambda 1 vn. You see, in this case, I can write V1 as a linear combination of all other vectors. In some sense, it says that all information